start. So it's a pleasure to have Dmitry Sorokin from ANZGSF Padua to talk about aspects of maximally symmetric nonlinear ModMax electrodynamics.
Okay, thanks very much. I would like to thank Gabriele for this opportunity to talk in Australia. I hope that it will be possible also to meet in person next year probably. And so today I would like to talk about some series of work which I did in collaboration with Igor Bandas, Kurt Lechner, Pier Alberto Marchetti, Andrea Sainaghi, and Paul Townsend on this theory which we called ModMax electrodynamics. So let me start from some introduction. As I actually learned myself only a couple of years ago, there is a huge activity on models of nonlinear electrodynamics, and they have been intensively studied in different with different applications. So they were introduced in different lines of research, from cosmology to condensed matter and optical materials. But probably the theorists like we who worked towards strings theory basically know two main examples. One of them is the Born-Infeld electrodynamics, which was the first nonlinear electrodynamics proposed in the 1933, and it was invented to make the finite energy or self-energy of charged particles such as electrons. But as we know very well, it found very profound implications in modern string theory. And then there is another famous example, which is Euler-Heisenberg effective theory of quantum electrodynamics, constructed in 1935. But then it turns out that there is a number of other models of nonlinear electrodynamics which came under different somewhat curious names like logarithmic, double logarithmic, exponential, racial, inversal, arc sign, power law, and other electrodynamics proposed by different people with different purposes. And the newest example of these models is what we call ModMax. We found it in 2020. And the peculiarity of this model is that it is a unique extension of Maxwell theory that preserves all its properties. That is, of course, Lorentz and gauge invariance, but on top of that, also electromagnetic duality and conformal invariance. It's somewhat surprising that this model has not been found before, because people studied nonlinear electrodynamics with electric magnetic duality as well as conformal invariance, but somehow nobody asked the question what happens when these two properties come together. And it turns out that it's very surprising fact, because the amount of models of nonlinear electrodynamics which possess electric magnetic duality is infinite, and those which possess conformal invariance also infinite, and they somehow converge into basically a single model when both of these properties are required. There is another model of Bielyanitsky-Biruля, which I mentioned later, but this model does not contain Maxwell theory in its decoupling limit. So today I would like to review some main peculiar features of ModMax electrodynamics. I would like to present some solutions, exact solutions of its equations of motion, and discuss some applications and implications of this theory, for example, in the context of charged black holes and also in TTbar deformations of conformal field theories. So let me start by setting up the stage, of course, and present, of course, very well-known results. Not results, but notion like Maxwell electrodynamics and its theory, symmetries. So just to be sure, do you hear me well?
Yeah.
Okay, so the action of Maxwell theory is, of course, very well known. It can be constructed in a Lorentz covariant way with the use of electromagnetic stress tensor, which is the curl of the four-vector potential. And here I also introduced the electric and magnetic component of this tensor. And the theory has very well-known equations of motion, and to which I added the Bianchi identity, where by F tilde I will denote the Hodge dual of the field strengths F mu nu. And we can rewrite these equations of motion, of course, in terms of electric and magnetic field. And what is interesting about this theory, that its action is invariant not only under Lorentz transformations, but under more general conformal group. I will here only present the, for simplicity, how the action is invariant under rescaling of space-time coordinates and the potential. So if we rescale x by multiplying it by a scalar a constant a, and then rescale the potential with inverse a, then one can immediately see that the action is invariant under this rescaling transformation. It can be also shown that the whole conformal group is the symmetry of this action. But then on top of that, the equations of motion of Maxwell's electrodynamics is invariant under the SO2 duality rotations of electric and magnetic fields. And so if you just rotate F prime, rotate the field strengths and its dual under the SO2 transformation, then we see, of course, that the equations of motion are invariant under these transformations. The action itself is not invariant, but it has certain properties which ensure these invariance that we will see later on. There are formulations of the theory in which the duality invariance lifted to the level of the action, but I will not talk about this approach here. So now let's introduce what we mean by nonlinear electrodynamics. The general structure of the action is as follows. It is in 4 dimensions. There are only 2 independent Lorentz invariant combinations of the field strengths, which one can construct, and one can choose them to be a scalar S, which I normalize with -1/4, so that S is just the Lagrangian of the Maxwell electrodynamics. And there is also the pseudo scalar, which one can construct by the linear combination of F and F dual. And so the most general Lagrangian of the nonlinear electrodynamics depends on these two invariants, and we will not introduce the derivatives of the scalars of the field strengths to avoid higher derivative terms in the action, and to avoid ghosts. A common assumption about the structure of the Lagrangians of this theory is that in the weak field limit, that is when the higher orders of F are less than the F squared, then the action can be written as a series in terms of powers of F, and the first term in this expansion is the Maxwell Lagrangian. But as we'll see, some models don't satisfy directly this condition, and one of these models is ModMax. The structure of the higher order terms in this Lagrangian, they depends on, of course, on the form of the Lagrangian itself, and it depends. They depend on the origin. For example, if you look at these terms in the Heisenberg-Euler theory for the spinor QED, then the coefficients A and B are related and have the following values here. So they are very small because of the weak fundamental constants which compose these constants. Then in the case of the scalar quantum electrodynamics, these coefficients are as follows, while in the case of Born-Infeld theory, which I will now discuss, they are equal to each other. Either any questions about this part? Okay, if not, I will proceed. And we, of course, would like that these nonlinear electrodynamics models are good models in the sense that they are unitary and causal theories, and this imposes some conditions on the Lagrangian, and one of these conditions which is required by causality and unitarity is the so-called convexity condition of the Lagrangian. This convexity condition means that if we take the Hessian matrix, that is the second derivative of this Lagrangian with respect to the components of the electric field, then the eigenvalues of these matrix, all of these eigenvalues should be non-negative. This is a requirement of convexity, which also allows to make the Legendre transform of this Lagrangian to the Hamiltonian formulation. Otherwise, it's not possible. Of course, if we consider a generic Lagrangian of this kind, then it's neither has a conformal invariance nor duality invariance in general. But one can, if one requires that the conformal invariance, then the Lagrangian should be a homogeneous function of degree 1. For example, if we scale these two scalar and pseudoscalar S with a parameter A, then the Lagrangian should be equal to itself times this scalar factor, because then it can be compensated by the rescaling of the measure in the action. So in general, this Lagrangian then can be written in the form of Maxwell's Lagrangian times some function, which is the ratio of P and S. On the other hand, if we require that the equations of motion of the theory are duality invariant, then what we require is that now the equations of motion have, you see, this nonlinear form, which I wrote with the coefficient -2 in the case of the equations of motion, just to ensure that when the Lagrangian is that of the Maxwell, one immediately gets the standardly normalized Maxwell equations here. So we would like that these equations of motion are invariant again under the SO2 rotations of the equations of motion with the dual field strength. So there is a typo here. There should be -2 as well in this part of the transformations, of course. So the duality invariance takes place if under this nonlinear transformation, which acts on f itself, because the derivative of Lagrangian depends on f and ft itself. So what we require is that after this transformation, we get the equations of motion, which can be seen as those obtained from the same Lagrangian as before, but with the transformed field strengths. And this imposes the condition on the form, this kind of differential conditions on the form of the Lagrangian. They were first found by Vilanitsky-Birula in 1983, or these conditions can be transformed to the conditions on the derivative of the Lagrangian with respect to the S and P here. So this is the general requirement for the theory of nonlinear electrodynamics to be duality invariant. Other questions at this point?
Ima, can I ask you a question?
Yes,
so
please.
The causality and unitarity conditions, so they don't involve any derivatives with respect to the magnetic field?
No, because electric field contains the time derivative of the potential, and causality and unitarity are related to the correct signs of the kinetic terms, as we know. The relative coefficient of the kinetic terms should be, say, positive or negative, right, in the action. While magnetic fields, they are like they contain only the special derivatives of the potential, so they don't cause these kind of problems. So here, instead of the variation with respect to the electric field, I could just put the variation with respect to the derivative of the vector potential, time derivative of the vector potential. That's the idea.
Thanks.
Okay, so now let me present the Born-Infeld electrodynamics, of course, the very well-known theory especially for people working in string theory and related topics. So here we have a dimensionful coupling parameter T, which has the dimension of energy density, and in string theory it determines the tension of the so-called three brane. So I present this Lagrangian in two different forms. So the second one is just the explicit expression for the determinant written to the left, which will be useful in what follows. And then you see that this Lagrangian, when expanded in series of the powers of field strengths to the fourth order. We have here the unique coefficient in front of the fourth order terms, and this is a manifestation of duality invariance of this theory. So this was proved by Bielyanitsky-Birula in '83. So this theory is duality invariant, but not conformal, of course, because of the structure of this Lagrangian and the presence of the dimension constant. In the weak field limit, that is when the tension parameter goes to infinity, we of course recover the Maxwell theory, which can be seen from this series expansion. I put weak field limit in somewhat in quotation marks, because this limit only means that what is written here, that f squared is greater than or vice versa, the higher powers of f are weaker than f squared itself. But for example, if f squared equals 0, it does not mean that the electric and magnetic fields are weak. These are just fields which are called null, and the electromagnetic waves satisfy these conditions. So the weak and strong field limit is somewhat jargon here, I would say. On the other hand, one might try to take the strong field limit, that is, take the tension of this the parameter t to 0, but what we find then, that the Lagrangian, because of the minus sign of the fourth order term here, it becomes purely imaginary but total derivative. So in the Lagrangian formulation, this limit is not well defined, but it turns out, as Bielyanitsky-Birula showed in his paper, that this limit is very well defined if we go to the Hamiltonian formulation of this theory. And in this way, one gets conformally invariant and duality invariant theory with enhanced duality symmetry. This duality symmetry gets enhanced to SL2R, and this theory is called Bielyanitsky-Birula theory. And the interesting property of this theory is that it has infinite number of conserved currents. So it might be integrable, but nobody has studied it yet for some reason. But this theory does not, actually this theory describes these null fields for which f squared equals to 0 and f of tilde equals to 0. So it does not include the whole Maxwell theory as a subsector. I will not have time to discuss this theory, and now I will pass to this ModMax electrodynamics, with the second unique example of the theory which possesses duality invariance and conformal invariance and has Maxwell theory in the free field limit, so to say. So let me give the Lagrangian for this theory. So you see, the Lagrangian has two terms. The one is the Maxwell term, and then there is the square root of these two Lorentz invariants here. And duality invariance of this Lagrangian requires that the coupling parameter gamma, which is dimensionless in this theory, enters through the cosine gamma and sine gamma in this way, in this theory. So one can check that this theory is duality invariant because the Lagrangians satisfy the duality invariance condition, and it is also conformal because of the structure. At least the fact that it is scale invariant is obvious from the structure. Probably it's not so obvious about the whole conformal group, but can be checked that it is indeed true, for example, by coupling this Lagrangian to external metric and show that the resulting Lagrangian is invariant under local while rescalings of this metric. So what we see here is that when gamma equals 0, then we get the Maxwell theory because the hyperbolic sign is 0. In this case, we recover Maxwell's theory, and this requirement of convexity, which I mentioned before, imposes the condition that gamma should be greater or equal to 0 in this theory. Since it's conformal invariance, then its energy momentum tensor is traceless, which one can see by computing it explicitly. So what we have in this theory is that the energy momentum tensor is just the Maxwell energy momentum tensor times this scalar factor. And here you see that there is the square root goes into the denominator. That means that the signal of non-analyticity of this theory when f squared and f tilde equal to 0. So I will discuss this on the next slide a little bit in more details. And so let me present the equations of motion of this theory. So again, you see that the equations of motion have this form, and there is the non-analyticity factor here, which means that these equations of motion are not well defined when S and P equals to 0, because depending on how we take the limit, for example, the ratio of S with the square root of S squared plus P squared can change from -1 to +1 because of this 0 divided by 0 ambiguity. There is no singularity, but the ambiguity here. But anyway, it should be stressed that the vacuum solution for which f mu nu equals to 0 is a well-defined solution of these equations, which one can check directly. So what happens with the case when S equals 0 and P equals 0? As I already mentioned, these are called so-called null fields. And for example, plane wave solutions, plane wave electromagnetic waves satisfy these conditions. So for plane waves, we have S and P equals 0. And so these are not well-defined solutions in the Lagrangian formulation of the theory, but it turns out that if we go to the Hamiltonian formulation of ModMax, then these null fields, and in particular plane waves, are exact solutions and well-defined solutions of this theory in the Hamiltonian formulation, because there is no singular, if you wish, ambiguity in the Hamiltonian equations for the fields which are null here. But what kind of solutions one can have in this theory? Of course, it's highly nonlinear, and it's difficult to find and some explicit nonlinear solution of these equations, but at least one can see that these equations reduce to linear Maxwell-like equations if the scalars P and S are related to each other through a constant factor like A. Then if we require also that S has a definite sign, then the equations of motion just reduce to Maxwell's equations. So if there are some questions at this point, okay, at least do you hear me?
Yeah, we hear you.
Okay, good. So let me now discuss some equations of motion of this kind. And it's interesting to have a look even at the equations, at the solutions which correspond to the coupling of this theory to electric and magnetic sources. So let me generalize these equations of motion of this theory by adding some electric charge and magnetic charge. In particular, we can consider point-like dionic particles which have the electric and magnetic charge, for example, Q electric and Q magnetic. So we can look at the simplest case when this dion is static, and because of the properties of the electric and magnetic field created by this with dion, it turns out that it satisfies this condition that P equals P is proportional to S. So in more detail, if you have a look at the electromagnetic field created by the static dion, in terms of the one form, it's easy to write down the form of the one form of the potential for this dion. So to satisfy the equations of motion of ModMax theory, it turns out that the electric part, that is the Coulomb potential of this dion, should be rescaled with respect to the one in Maxwell theory by this factor e to the minus gamma, while the magnetic monopole field proportional to the magnetic charge Q is standard, where cosine theta and d phi theta and phi correspond to angular coordinates, spherical coordinates of three-dimensional space here. And now, but we can do more. We can consider the dion which is moving in space and with some acceleration, and look at the Lienard-Wiechert fields created by this dion. I will not write down the structure of these fields here, but
Dima, sorry, can I ask a question? So
yes,
these sources, J, E, J, M, I mean, are they just delta function sources?
Yes, yes, in this example which I am considering, yes, they are just delta functions multiplied by the velocity of the particle, the standard ones. Yes, the standard currents of the point-like particles. So now we may compute the Lorentz force which act by Lienard-Wiechert fields created by the dion with the charges Q, E, and Qm on some test dion with which has the charges electric charge Q and magnetic charge G, and which moves in the with the momentum p mu and the speed v mu. Then we know that the Lorentz force, which describes the acceleration of the particle. And for this particular configuration which we are considering, it has the following form, where f mu nu, f mu nu tilde, as I said, they are linear, they are certain Lienard-Wiechert fields created by the dyon. And you see again where the difference between Maxwell theory and ModMax electrodynamics appears here. So we have the e to the minus gamma factor in front of the terms which describe the basically the Coulomb law for electric and magnetic charges here, while there is no any rescaling in the interaction between electric charge with magnetic charge and vice versa. So that's so the point here is that one might try to say that, for example, we can rescale the electric charge here so that everything would look like in the Maxwell electrodynamics. And but what happens? You see this from the Lorentz force, that if we scale the charges in one place, they will reappear in another place. So it's not possible to completely rescale. Get rid of this factor by rescaling the charges for the moving objects here. So let's proceed.
Sorry,
yes?
can you go back to that slide?
Yes.
So, Lienard-Wiechert potential, it has non-trivial time dependence, and here
yes, it has, of course.
It's hidden here, or
yes, I have not written it explicitly, but f mu nu, of course, it's the standard. So what we are considering Lienard-Wiechert field strength f mu nu, which has say the canonical form. Which depends, of course, on time, and we consider the motion of another dyon in this electromagnetic field created by the Lienard-Wiechert fields.
Mm-hmm.
So this tau here, which is the tau, this is the wall line of this test dyon with the charges QG, which moves in these electromagnetic fields created by another dyon.
All right.
Okay, so this dyon configuration can be promoted also to the black hole solution, and people studied these black hole solutions in the ModMax theory. So, for example, tau knot solution, right, and Nordstrom black holes and others in the presence of ModMax electrodynamics. So what we do here, we couple ModMax theory to Einstein gravity, for example, then we have the contribution to the energy momentum tensor of ModMax here, and we are interested in black hole solutions, for example, the spherical solutions like Reiser-Nordstrom black hole, whose metric has the standard form with this FR, some blackening factor. And now we look for a Reiser-Nordstrom black hole solution in this case, which is nothing but the example of the dyon, which we considered in the previous slide. So the electromagnetic potential of the black hole has this form here, and one can compute the factor FR for the black holes solving for the equations, Einstein equations, and we see again that here there is this rescaling factor e to the minus gamma, which appears in in the form of the function fr. So the horizon, of course, of this black hole is when this function is 0, and so the black hole has the two horizons, and we see that here the extremal black hole, when the two horizons coincide, is responds to the mass squared of this black hole to be equal not to the q squared, but q squared times e to the minus gamma. That is, there is some screening effect, and the mass squared can be actually of the extremal black hole can be less than the square of its charge. Okay, so this is the what I wanted to say about black holes. If you have some questions at this point, please ask. If not, let me consider some other physical effect which is quite which is usually studied in nonlinear electrodynamics. So this is effect which, for example, in the case of ModMax theory, does not depend how we rescale the charges here. It is manifests itself independently of the physical meaning of the charges, and this is so-called birefringence. Birefringence is a very well known phenomena in optical physics, and it consists in the fact that if we have some anisotropic optical material with some optical axis, then when the ray of light enters into this material, it splits into different rays propagated with some different dispersion relations, and this splitting depends on how the light is polarized with respect to the optical axis. In the case of nonlinear electrodynamics, the strong background electromagnetic fields play the role of these anisotropic optical materials. For example, if we consider a strong magnetic field, then the propagation of fluctuations, some plane waves in this background in nonlinear electrodynamics in general produces the effect which is very similar to birefringence. So how do we compute this effect in nonlinear electrodynamics? We split the field strength of the electromagnetic field into the background external part, which I call F external, plus some small fluctuations, and then we compute the Lagrangian for the fluctuating part up to the second order, so that we linearize the theory around this background, and if the background is constant or homogeneous, then there is no derivatives acting on this background, but it acts only on the fluctuation part. But there is this tensor lambda mu nu rho sigma, which depends on the background fields whose structure depend on the form of the Lagrangian. And as I said, we are interested in, for example, in propagation of some plane waves in this background, and to study the effects of polarization of light in this kind of backgrounds. So we take the plane wave solution. We would like to consider what happens with the plane wave in this background. So we consider the field strengths of this fluctuation to be that of the plane wave, where E and B are electric and magnetic fields of the plane wave, and E characterizes the polarization of this wave. So the picture is as follows. If we have the background magnetic field pointing in this direction, and the wave vector of the plane wave is k, which points in this direction, then k and b, of course, form a plane. And then the polarization characterized by the vector of the value of the electric field, it does not, in general, it is neither orthogonal nor parallel to the plane formed by K and B. And it turns out that there are two components, one which is parallel to the plane of K and B, and another one which is orthogonal to it. And these two polarization components, we can compute the dispersional relations for these two polarization components, and what we find that they are different in general. So from the equations of motion written here, substituting these ansatz, what we can compute the dispersion relations for omega squared depending on k, and the general structure of these dispersion relations is as follows. It is we have these coefficients and parallel and orthogonal here. These coefficients are called refraction indices. They depend on the wave vector of the plane wave and the background field. And so n parallel is the refraction coefficient corresponding to the polarization along the plane of K and B, and n orthogonal is respectively orthogonal to the plane. And what is birefringence? The birefringence is a fact when these two coefficients are different. So when there is when delta n is non-zero, then we have birefringence. Of course, in the case of Maxwell theory, there is no birefringence because n parallel and orthogonal are just equal to 1. So we have the standard relativistic dispersion relations. But it turns out that also for Born-Infeld theory, there is no birefringence. These coefficients, though they are not equal to 1, but they are equal to each other. While for the Heisenberg-Ehrenberg electrodynamics, delta has this small value, and it increases with the increase of magnetic background. T squared is just Tesla here. Now, what about the more ModMax birefringence? ModMax birefringence is has birefringence, and in this case, one of the mod, basically the one which is orthogonal to the plane, propagates with the standard light cone dispersion relation, while the second mod has this kind of dispersion relation where k squared multiplied by this factor cosine squared phi plus e to the minus 2 gamma sine squared phi, where phi is the angle between K and B. So the characteristic feature of Maxwell of ModMax birefringence is that it does not depend on the value of the magnetic background, but only on the angle between K and B. This is a manifestation of conformal invariance, basically. So if we compute the birefringence for ModMax for small gamma, then we see that delta is n is proportional to gamma itself. And if ModMax has something to do with the reality, then it's from the experiments on birefringence, which were the latest data about the birefringence experiments, which were carried out in a laboratory near Padova, they put the following upper bound on delta. So at 2.5 Tesla, the delta is less than some units times 10 to the 23rd. And you see that there is that 12 plus minus 17. So they did not actually measure the birefringence, but they put the upper bounds on possible values, from which we can see that gamma should be very small if it has something to do with reality. So that's what the birefringence tells us about the value of gamma. But of course, this is if we speculate on the possibility of this theory to have something to do with fundamental physics. But if the theory is considered to be an effective theory for some condensed matter or optical materials, then in that case, gamma can be much larger. Is there any questions at this point? Of course, this experiment, I should say, was not made because of ModMax theory, but they wanted to measure birefringence to confirm the predictions of QED or Heisenberg-Ehlers theory. So the hope is that with the further increase of magnetic fields, they will be able to finally find what is delta n. Now let me say some words about path from experiment to more theoretical points, and consider some generalizations of ModMax. So what we found actually that there is a Born-Infeld generalization of ModMax, or generalization of ModMax by Born-Infeld, and the Lagrangian of this generalized Born-Infeld theory has the following form. You see that this theory is again duality invariant, but of course not conformal, and it has two parameters. One is T, as in the Born-Infeld theory, and another one is gamma, as in ModMax theory. And basically, the ModMax Lagrangian appears under the square root of this theory instead of the Maxwell Lagrangian F mu nu. So we see, of course, that when gamma equals to 0, this Lagrangian reduces to the Born-Infeld theory, and when t goes to infinity, it reduces to ModMax theory. There is also a six-dimensional generalization of the theory. I will probably not go into the details, but just sketch the structure of this theory. So it is known that there is one can construct a duality, a self-dual theory for a chiral gauge 2 form. So in 6 dimensions, we can introduce a kind of 2-form electromagnetic potential A, and the 3-form field strengths, which in the linear approximation is self-dual. And for example, the M5 brane action contains this kind of field, and it turns out that the free action for this field, which is the first part of this Lagrangian here, can be extended to ModMax kind of chiral 2-form electrodynamics. Probably, since time is running fast, I will not stop at this point, but if there is some questions, I will be happy to answer. Okay, if not, let me mention the super. Oh, sorry. Somehow. Okay. Okay, what I wanted to show was the supersymmetric extension, but maybe I'll just say in words because I don't find the slide, which is probably hidden somewhere. And so as we did independently, Sergei Kozenko and our group independently generalized ModMax theory and generalized Born-Infeld to n=1 supersymmetric extension and found n=1 supersymmetric extension thereof. And moreover, Sergei has constructed higher spin generalizations of this theory, and also a kind of n=2 supersymmetric extension, which I think for some reason is not conformally invariant though. So there is a problem. Maybe he might comment later on this. So the supersymmetric extensions are known, but let me finish probably in, well, hopefully not finish with this, but mention another interesting topic which appeared with respect to this ModMax. It is the relation of ModMax to so-called TTbar deformations of Maxwell electrodynamics. So the TTbar stands for halomorphic and anti-halomorphic part of the energy momentum tensor in two-dimensional conformal theories. So the TTbar deformation was put forward by Zamolodchikov for deforming two-dimensional conformal, in general, quantum field theories, and in particular conformal field theories, with the use of some composite operators, mainly irrelevant operators, which are bit of components of the energy momentum tensor. And they found very interesting developments because such kind of deformations preserve nice properties of the initial quantum field theories in two dimensions, for example, integrability and renormalizability and others. And later on, these kind of deformations were generalized to higher dimensions by several groups. For example, and these TTbar deformations have the following logic. One starts with some theory with a Lagrangian L0, which for some fields phi, and then add the term linear in some coupling constant lambda with some operator constructed with the components of the energy momentum tensor of the initial theory. Then one adds the second order term lambda squared with the energy momentum tensor constructed from the theory obtained at the linear order of lambda, and so on so far. And it turns out that the final Lagrangian, which now depends on the coupling constant lambda, satisfies the following flow equation. So the derivative of lambda with this, of the Lagrangian with respect to lambda equals this operator depending on the energy momentum tensor. For example, for the Born-Infeld theory in 4 dimensions, it has been shown by various people that the variation of its parameter of its Lagrangian with respect to lambda is equal to the following combination of the components of the energy momentum tensor of the Born-Infeld theory, where lambda is inverse of the tension T. And it turned out that for ModMax theory, the situation is similar, in the sense that if you take the derivative of the ModMax Lagrangian with respect to gamma, then it turns out that it is the square root of its square root of its T mu nu of ModMax theory. And these kind of deformations were called root TTbar by Gabriele and his collaborators. And the picture also involves the generalized Born-Infeld theory. So what we have here is the following diagram, which closes on the generalized Born-Infeld theory. So we start from Maxwell's Lagrangian, and then we can TT-bar deform it using the conventional, let me call it lambda deformation. Then we arrive at the Born-Infeld theory. And then what we can do, we can deform further the Born-Infeld theory by the root deformation with parameter gamma, and then we will arrive at the generalized Born-Infeld theory. Or we can do a different path. We can start with Maxwell theory and go to ModMax theory via this root TT deformation of Maxwell theory, and then perform the conventional TT-bar lambda deformation of ModMax theory, and we again arrive at this generalized Born-Infeld theory. Some groups generalized these TT-bar deformation structures to other dimensions, in particular to two-dimensional theories, and Gabriele and his collaborators contributed to the development of this work, and there are nice generalizations to supersymmetric TT-bar deformations as well. Unfortunately, I don't have time to discuss this. I think I should stop at some point because time is. What do you think, Gabriele?
Yeah, now it's 1 hour since you started.
Yeah.
We wrap up in the next few minutes, and then we can.
Okay, basically I have the final slide and then the conclusion. Because what I wanted to discuss in this final slide is the possible, some hints about possible origin of ModMax theories and effective field theory. So, of course, as all nonlinear electrodynamics, they should be considered as some kind of effective field theories or limits of some fundamental theories, and it would be interesting to understand what is the origin of this ModMax theory, and probably the following alternative formulation of its Lagrangian may help to understand its origin. So we can actually remove the square root from this Lagrangian by introducing the auxiliary scalar field into the game. So you see that I can rewrite the Lagrangian in the form where we have the kind of Maxwell-like term plus the topological part, and here there is the cosine phi and sine phi contribution of this auxiliary field here. The field is completely auxiliary, so if we integrate it out by solving its equations of motion, we'll go back to the ModMax Lagrangian with the square root. But an interesting observation, I think, here is that this Lagrangian is similar to the Lagrangian of the Maxwell electrodynamics coupled to the dilaton and axion field. Of course, the dilaton and axion field, they have kinetic terms, while here phi is completely auxiliary. But let's suppose that also gamma is some expectation value of some second field, gamma x, then when we compare these two Lagrangians here, we see that the A and phi and gamma and phi curled are nothing but the field redefinitions here. So we can relate the dilaton and axion to gamma and phi by these relations which are invertible. So the question now is, is there some potential here which causes one of the axion of this combination to acquire an expectation value, and while in a certain limit we can neglect the kinetic terms of these fields, and then we are arrive at the ModMax Lagrangian. So these are things to think about. And so let me conclude as I tried to show you in the review that nonlinear electrodynamics has a rather long history, and it's continuing to be a very active field of research in applications in different spheres of physics, from cosmology to plasma physics. And as I said, almost all or all nonlinear electrodynamics should be considered as effective field theories, and we know very well the origin of some of them, like Born-Infeld and Heisenberg electrodynamics. So for these theories, we know that they come from string theory and quantum electrodynamics respectively. But for other theories, it's not so clear, though there is some possibility of relating the models of nonlinear electrodynamics in 4 dimensions to a Kaluza-Klein dimensional reduction of multidimensional higher curvature gravities related to string theory, which have been shown by Dimas and Herdeiro in 2000. And so as I tried to say in the last slide, it would be interesting to understand the origin of ModMax electrodynamics, whether it has something to do with the axion-dilaton coupling in some more fundamental theory or not. And finally, there may be some interesting developments and more profound insight into the implications of the root TTbar deformations of ModMax and generalizations. And there are other interesting problems, I think, which can be studied in these directions, and the work is in progress. So thank you very much.
Thank you very much, Dima, for the very nice talk. Are there questions from the audience?
Can I ask you?
Yes, sure.
I have comment and a question. I mean, the comment, well, Dima, you mentioned that in the past people didn't ask question of combining duality invariance and conformal invariance. But there was work on combining duality invariance and superconformal invariance. Well, in the year 2000, this is my work with Stefan Tyson. We were interested in just effective action for n = 4 superiomics. So basically, work out perturbative procedure to construct the action, but n = 2 superfields a bit complicated area, so we didn't end up with closed form action. So
no, yeah. Yes, please. Sure.
Yeah, and just and question that was comment, but I mean question. So what? Well, just you take ModMax, reduce it to 3 dimensions. And then you'll get a scalar and vector, and then you dualize vector into scalar. You'll end up with some sigma model. What kind of sigma model is that?
Well, I think it would be interesting problem to have a look at.
So you don't know answer, yeah?
I don't know the answer. Maybe I don't know. There were some studies of a kind of two-dimensional. Well, you want to be in 3 dimensions, right?
No, in 3 dimensions you can dualize vector into scalar. So when
Yes,
when you dimensionally reduce, you get scalar.
Yeah. No,
And
no,
then
yeah, I
you
understand.
dualize vector also.
Yeah, no, I don't know. I have not had a look this problem, and I don't think anybody did. There were some work on 2-dimensional reductions of ModMax by several groups, including Gabriele's, I think. So in 2 dimensions there are with scalar fields, and there are some analogs, but in 3 dimensions I don't know.
Okay.
It's a good question to solve.
Yeah.
So, Dima, can I ask you, I mean, a question that probably you receive at every talk, but can you comment on the quantization of this model and whether you expect...
Yeah, quantization is an interesting thing here, and probably not very easy thing to do. Again, maybe this action with the use of the scalar field might be useful, because there is no square root, maybe this kind. Or one can study some effective action of ModMax in some background, using the background field methods to compute the one loop, for example, effective action of the theory. I think this is doable, and one can start with the analysis of this of these things.
Any more questions?
Can I ask one related question, if there's time?
Yes, please.
So about this auxiliary field formulation, I'm curious, because since there exists a combined Born-Infeld ModMax theory that you showed us, I'm curious about whether there's some way to engineer, say on a brane in string theory, some background which would have turned on both ModMax and the Born-Infeld coupling. So do you suspect that such an engineering might be related to this auxiliary field formulation, so that maybe it arises from some coupling between the gauge field on the brane and some ambient scalars like a dilaton or axiodilaton?
Yeah, well, that's actually the question. Well, the question or the problem, how do you call it, is very interesting, and we discussed it with Paul Townsend a little bit, but without developing anything. So yeah, there is. I think you are right. This is a question which is very interesting to see if these kind of couplings come from the scalar fields may come from the couplings of the vector field or to the scalars on the brane, but I don't know yet how to realize this idea. Yeah,
Can I ask you a follow-up
Yes.
question on this? So the auxiliary field formulation that it's in this slide, do we have an extension to the gamma Born-Infeld case, or it's?
Well, no, we did not study it. Probably there might be some extension, because there are some. I think Arkady Tsetlin and probably with Rochek, I think. Maybe Sergey can comment on that. They, in one of the papers, they have rewritten the Born-Infeld using auxiliary scalar fields. I think they had 2 or 3 of them. I don't know. Also here, actually, we can introduce 3 scalar fields. And in the last paper on the solutions of ModMax, you can have a look. We presented different forms of this the Lagrangian with 3, 2, and 1 auxiliary field. So depending on maybe not 1, but maybe 2 or 3 are better. I don't know. But in principle, yes, I think it's possible also to do similar things with the generalized Born-Infeld.
Any more questions for Dima?
Just one comment. This Dima, you mentioned this work on higher spin extensions of ModMax. It's joint work with Emanuel Raptakis.
Mm-hmm. Yes.
So he's also present.
Yeah, sorry. Of course, I mentioned also Gabriele, but not all. But not all of his